In the first part of Notes 15, we looked at an example that sort of illustrated what an ANOVA test is doing, but we didn't get a chance yet to talk about what an ANOVA test really is and how you would do one of these on your own. So first off, ANOVA is actually an acronym that stands for Analysis of Variance. So you can see I've highlighted the key parts there. And as we've seen, it's a technique that we can use if we want to compare two or more population means. And right away I like to acknowledge that this does seem a bit odd, since it's called the analysis of variance, not the analysis of means. And this is something that people sometimes get tripped up on a little bit. So over the next couple pages, we're going to investigate why this name actually makes sense. Like, what are the variances that we're analyzing? And how do those allow us to make conclusions about population means as our sort of end result? So as you recall from part 1 of the video, this is the example that we're working for. We've got a company that has 4 different package designs for a cereal, and we recorded the number of cases that they sold, and we're trying to decide if there's a difference in population means between the different package designs. So we already addressed this question a little bit in part 1. If we wanted to compare the population mean sales for the 4 designs, and so far we've only learned about how to do a 2 independent samples t-test, how many different tests would we actually have to perform? And you could try to list them out. We could do A versus B, A versus C, A versus D, B versus C, B versus D, and C versus D, which means we would have a total of 6 different 2 independent sample t-tests. So that would take a bit of time. And as you added more and more groups that you were comparing, the number of tests that you would have to do starts growing faster and faster. And so having something like the ANOVA test that can save us a lot of work is going to be really useful for us to answer all sorts of questions where we don't just want to compare 2 groups to one another. So let's start with setting up our hypotheses for an ANOVA test. We said that we're comparing population means, and our null model always says that there's nothing going on. So for the case of an ANOVA test, our null model is going to say population mean, in this case, A, equals population mean B, equals population mean C, equals population mean D. And I'm writing A, B, C, and D here to correspond with package designs A, B, C, and D. But if you had, say, 6 groups for your test, you would have 6 population means that were all equal to each other. If you had 3 groups, you'd only have 3 population means that were equal to each other. So that's the null hypothesis, nothing going on. The alternative hypothesis is a little bit trickier, because up to this point, what we would have done is we would have just taken those equal signs, maybe turned them into not equal signs, and said, well, the opposite of mu1 equals mu2 is that mu1 does not equal mu2. But in the case of an ANOVA test, for the null hypothesis to not be true, we don't actually need all of the population means to be different from one another. We just need at least one pair to be different. So for example, it's entirely possible that package designs A, B, and C, they don't matter at all. No matter which one you use, you would sell the exact same number of cases of cereal on average. But maybe package design D is different. So instead of putting that all of them are different, we actually just write it out in words for the alternative hypothesis. And we say the alternative is that at least one population mean is different from another. So null model, all population means are equal. Alternative model, at least one of those population means is different from another one. And as I mentioned, how many population means you have depends on how many groups you're comparing. And the reason we can't just add those not equal to signs is because we don't need all of them to be different. We just need at least one pair to be different. So once we've set up our hypotheses, usually our next step is to calculate some sort of test statistic. We saw in part 1 that that's going to be called an F statistic. We're going to compare our data to our null model that says all of our groups have the same population mean. And it's going to look a little bit weird when we do that. So this is sort of the simplified version of our test statistic. We're going to take something that we're calling MSB. We'll see what that stands for later, but basically is a stand-in for the average variability between our groups. And we're going to divide MSB by MSW, which is the average variability within our groups. So how to actually find MSB and MSW, that gets a little more complicated, but this is sort of the shortest way to think of our test statistic. How much are our groups varying from one another, divided by how much variability is there within our groups. And hopefully you're already starting to make the connection that when we call this an analysis of variance, it's because we're comparing these two variabilities. So the question is, how does that allow us to say whether our population means are different from one another? And so that's what we're going to explore a little bit coming up here. And we're really not going to calculate this whole messy equation by hand. You'll see what the MSB and MSW parts look like on the next couple pages. But I want you to see where these numbers are coming from so you have a sense of why this is actually working. And we need a little bit of notation to do that. So we've worked with X bar before, that's our sample mean, and N as our sample size. But remember that we've also got multiple groups. So just like in the two independent samples problems, we had X bar 1 and X bar 2, we might have 4 of those or 6 of those. And so I'm just going to say X bar with any little subscript is the sample mean for that group. And then same thing with sample sizes. I might have multiple groups. I want to know how many people are in each of those groups. And so N with a little subscript is the sample size for that group. And then lastly, we're going to use a capital I to tell us the number of independent groups that we have. And one thing you want to be careful about in these notes is that I's and 1's and L's all sort of look similar. So make sure you're getting the right thing in these equations when you look at them. So let's look at MSB first. MSB stands for the mean squares between. And as we said, it's a way for us to measure the average variability between our groups. So to do that, we're going to compare the mean for each individual group to the overall mean. And I have a picture below that sort of illustrates that idea. Each of the red stars here is the mean for that group. So for group 4, you can see my data values here. This red star is the mean of that group. And I want to see how far that red star is away from the overall mean for my data. And by doing this, if these bars that I drew with the dark blue line are big, that means there's quite a bit of variability between my groups. My groups look pretty different from one another. If that bar is small, so like this one's pretty small, then there's really not much variability between my groups. All right? So this is our first step. We want to know how far do the group means differ from the overall mean. And the way that we actually calculate that is this formula here. Now, we're not actually really going to do this by hand. SAS will calculate these things for us. But you'll notice that this bar that I drew is represented in each part of the formula by the sample mean for that group minus the overall sample mean. So in some sense, I'm taking each of these 4 bars and I'm putting them together into a formula to tell me some sort of overall number that says how much do these groups vary from one another. I'm also going to point out right now that this top part we refer to as the sum of squares between. This will come up again later in the notes. And on the bottom of this, this is an I minus 1. So the number of groups minus 1. And if you actually wanted to calculate this just to see what it looks like worked out, I've got the data in SAS On Demand. It's called 15-serial. And I can open it up here real quick. Let me open a new file, because some of you may have noticed that if you edit these files, SAS gives you some errors and things occasionally. That's because it's a shared file, and so we want to edit our own file. And you'll see the numbers that I'm going to use on the next page. So here are my sample sizes for each group. Here are my sample means for each group. And if I go back to the notes, you can see I've just plugged those in and worked through the math, and you end up getting 196.074. So essentially, in some way, the variability between groups can be described with this number. Now, I don't have any context at this point to know if that's a big number, small number. So what we're going to do is we're going to look at the variability within groups, and we're going to compare the two. And so we're going to see, is there more variability between their groups than just what I'm seeing as kind of random variability that's happening within the groups? And just to make sure that you're sort of following this process, I've got a question down here. What if I had had 5 independent samples instead of 4? How is that going to change this equation? And you might notice that this part here, I'm just going to add another one of these that says n5 times x bar 5 minus x bar squared. And then I would be 5, so I would have 5 minus 1 on the bottom. And you can see that change happening here. So let's take a quick look at the mean squares within as well. MSW, we said, stands for mean squares within. It's a way for us to measure the average variability within our groups. And in this graph, I got rid of the overall sample mean, because I don't care about it now. I just care about inside each group, how much do my individual values differ from one another? And you can see in this group that you can kind of go from each number to the star and get a general sense of how spread out that group is. You could do the same thing in group 2, group 3, and group 4. But up to this point in the semester, if I said, tell me how you would summarize the variation or variability in a data set, we've seen standard deviations and we've seen variances. So we can actually just use the standard deviation or the variance for each group. And if you go down here, you'll notice that that's exactly what we're doing. Kind of like with mean squares between, we're taking some information from each group that tells us how spread out that group is. We're putting all of that information to try and get a sense of how spread out the data would be if we weren't even considering package designs, if package design didn't matter. And I've got a note here that if we only have 2 groups, this is actually the pooled standard deviation from our 2 independent samples test. So again, this is another way that we can see that this is really just an extension of that test from before. And I'm not going to go through all of these numbers. You can do it if you would like, but this is the standard deviation for group 1, and then I squared it, standard deviation for group 2, and I squared it, and so on. And you can see that my mean squares within my groups, so how much variability there is within the groups, is only about 10.5 compared to this 196 that I had between groups. So again, we're going to need to learn a little more to put this into proper context, but it seems that there's quite a bit more variability between the groups than there is within the groups. And that's going to be an important thing that we'll come back to on the upcoming pages. So just to make sure you're following along with the equation up here, if I added a 5th group, what would happen? Well, just like before, I would take one of these terms, I would add it to the end, so I would have n5 minus 1 times s5 squared, and then I would add my sample size for my 5th group. This is an I in the formula. That's my number of groups, which would now be 5. So for this set of the second part of Notes 15, I want you thinking about what is this test statistic and how are we comparing the variability between the groups with the variability within the groups, and what might we do with that? When we pick back up with part 3 of the video, we'll actually look at how we put it together to get our test statistic, and how we decide if that variability between the groups was big, small, somewhere in between, and how that might help us reach conclusions to answer the types of questions that ANOVA tests allow us to answer.